Hello everyone. In this lecture, we will carry our discussion forward and we will talk about self-adjoint or Hermitian operators. Self-adjoint or Hermitian operators. We had already I had given you all a brief introduction to this when we were talking about the operators, the properties of linear operators. So the basic idea is here, the adjoint of an operator. We have to take the idea from here. That is, if suppose I have some operator A, okay, let's say I'm having some Hilbert space, okay, so let's say there is some Hilbert space, and on this Hilbert space there is some operator A which is defined on this one, okay, there is some operator A, linear operator A, which is defined on this. Then this operator will have a corresponding adjoint, something called as an adjoint. Okay, this operator will have something called as an adjoint, which is represented as a dagger. Okay, this is a dagger, and this a dagger, the property is, suppose I take any two functions, any two vectors. Okay, let's say f and g. Okay, I have any two vectors in this vector space, okay, so f and g, and this a I want to operate on this one, the scalar product. So let's say I have f and I have g, and I apply a on this one, okay, then the adjoint is such that the same pair of vectors, so we have f and g, if I apply the adjoint on, if I apply this a dagger on f, so I'm applying a on g, and if I apply a dagger on f, and if the result happens to be the same, then we say that this a and a dagger, they are adjoints of each other. Okay, they are adjoint of each other. So this is the meaning of the adjoint of an operator. If the operator itself, it happens to be the adjoint of an operator happens to be the operator itself, then it is known as a self-adjoint operator or a Hermitian operator. So an operator A is said to be self-adjoint or Hermitian if the adjoint and the operator f, they are one and the same. So if they are one and the same, then it really does not matter whether the operator, whether it operates on the right member or it operates on the left member in the scalar product. Okay, so this follows from the definition. This follows from the definition of an adjoint and the definition of a self-adjoint operator. Okay, so it really does not matter. You can just move this around. If I have a scalar product, f and g, if I have a scalar product f and g, then this operator a, okay, you could move this around. Either you could place this over here or you could place this over here, any way you want. Okay, then we say that this is a Hermitian operator. So then this brings us to important definition that you would have come across in your quantum mechanics, that is expectation value. So expectation value of an observable A in a quantum mechanical state is described by any normalized wave function. So any normalized wave function psi, that is going to be the vector, okay, just like your f and g. So we have the vector psi. Then we talk about the expectation values of operators. Okay, expectation values of what? Expectation values of operators. Always expectation values of quantum mechanical operator. We talk about expectation value of position. Position is a quantum mechanical operator. We talk about momentum. Momentum is a quantum mechanical operator. We talk about expectation value of energy, which is again the expectation value of the Hamiltonian operator. Okay, so expectation value is always for a, we find expectation value always for an operator. Okay, so the average value of an observable A in a quantum mechanical state, which is described by any normalized wave function, is known as its expectation value. Then of course I have to be more specific here. When I say average value, what kind of average are we talking about? We are talking about an ensemble average. So I'm sure you would have probably come across this in your quantum mechanics. So just for the sake of completion, when we say average, we mean the average of an ensemble. Okay. Okay, so this expectation value is defined in this way. So we say the expectation value of this operator A, it is simply the scalar product of, you take the psi, some wave function psi. So we are having some wave function psi, and on this wave function, if I apply the operator A, on this wave function, it will give me a new wave function. That wave function is A psi. You could call it A phi also if you want. Then if I take the scalar product of this one and this one, if I take the scalar product of these two, that is the scalar product of psi, okay, and phi. And what is phi in this case? Phi is nothing but a psi. Phi is nothing but your a psi. So psi a psi. This is how we define the expectation value of an operator. Okay. So take a wave function, operate this operator on the wave function, that is going to give you the new wave function. Then these two wave functions, find out the scalar product, that is the expectation value. So this is the expectation value. If the operator A corresponding to an observable A is Hermitian, then its expectation value is always going to be real. Okay, it can be proved very easily. If the operator A corresponding to an observable A is Hermitian, then its expectation value is real, and we are interested in operators whose expectation value is real, right? Because the real expectation value, that is what is going to correspond to, if the expectation value is real, that is going to correspond to your physical reality. Okay, so we would like our expectation values to be real. So if you would like the expectation values to be real, then the operator which corresponds, the operator whose corresponding operator whose expectation value you are trying to find out, that operator must be Hermitian. Okay, so now this can be proved very easily. So suppose for a scalar product between two vectors, we have this. This is a basic property of the scalar product. We have already discussed this. That is, if I have a vector f and a vector g, okay, we construct the scalar product. Then if I take this scalar product, if I take the conjugate of this one, then what will happen is we just have to swap this f and g, they will just get swapped. This star is going to vanish, then this f and g is just going to get swapped. Okay, so this is basic property of for scalar product of any two vectors. So now from this equation, that is the definition of the expectation value, okay, where we are assuming that A is Hermitian, from this we have this. So if suppose I want, because you remember this A is going to give me a number, okay, now this number can be real, it can be complex. So we can find out the conjugate of this one. So if I take the conjugate of the expectation value, so that is like a psi, you take the expectation value, and if you remember, this is just a fancy way of writing this. So if I say psi, okay, a and another bar and a psi, I mean this is just to maintain the symmetry. So it is just a fancy way of writing this. So this is the same as psi a psi. Okay, this is the same as psi a psi. So I have just removed this bar. Okay, we get rid of this bar. So that means what A is actually operating on the right side psi and taking the star here. Now from this property, whenever you take the star, any two vectors, if you take the conjugate of the scalar product, then that gets the order of the vectors that gets swapped. So this will come here, okay, and this will go over here. So as a result of this, we have this. This star is going to vanish. This star is going to vanish. This A psi comes on the left side and psi goes onto the right side, and we have this one. Now what have we assumed? We have assumed that A is Hermitian. We have assumed that A is Hermitian. So if A is Hermitian, that means A must be equal to A dagger. If A is Hermitian, then A must be equal to A dagger. So this A I replace with A dagger over here. Now the moment I replace A with A dagger, again go back to the definition of an adjoint. What is the definition of adjoint? We saw some time back. Adjoint means, okay, suppose I have a operator A, okay, and it operates on G, and then on this side we have some vector F. Then its adjoint is such that you can operate the dagger, that adjoint, on the left member, okay, leaving the right member the same. These two will be exactly the same. So that's what we have done over here. So here the dagger is operating on the left member, so we might as well get A onto the right member, and lo and behold, this is nothing but your expectation value, because this is just a fancy way of writing. I just put another bar over here. So this is nothing but your A expectation value of A itself. So if the conjugate of a number is equal to the number itself, then that means that number must be a real number. Okay, so this is basically this shows that if I have I have an operator which corresponds to an observable, then we want the expectation value to be rooted in physical reality. So that means it must be real, and for this to be real, it must be Hermitian. Okay, so this is the reasoning behind why we expect quantum mechanical operators to be Hermitian. Okay, so let me erase this and then move forward. Alright, so since for an Hermitian operator, A dagger is equal to A itself, okay, then A mu nu is equal to A nu mu star. Okay, this is basically the elements of the matrix. That is, let's say A is there, okay, and A I'm writing is as a matrix. So A, let's say 1 1, A 1 2, A 1 3, and so on. A 2 1, A 2 2, A 2 3, and so on. Okay, so let's say I write something like this. Then what will be A dagger? What will be A dagger? A dagger will be, dagger means you are taking the conjugate and you are transposing it. You are taking the conjugate and you are transposing it. That means you are taking the conjugate. So A11 star, okay, and you are taking the conjugate. Then this A12 will come over here. A12 star will be here. Then A13 star. Okay. Similarly, A21 star. Okay, and so on. This is what A dagger is going to be, and because these two are same, these two are equal, that means A21 and A12 star must be equal, right? Because these two are expected, they are said to be equal. So it means in general, if I take A21 here and here A12 star, A from these two, okay, from by comparing these, we find that A21 it must be equal to A12 star, and hence we get this expression. In general, in A nu mu must be equal to A mu nu star. So a matrix, and this is, if you remember, if you have from your course in linear algebra, you remember that such matrices which behave in this way, they are known as Hermitian matrix. So the matrix which represents an Hermitian operator is an Hermitian matrix. So from equation number 3, from this equation we also realize that the diagonal elements, they must be real, because the diagonal element, what is the diagonal element? The diagonal element is A11. It must be equal to A11 star, right? Because this is a diagonal and this is another diagonal. A11 must be equal to A11 star. So it means, this means that A11, okay, is a real number. It belongs to the set of real number. A11 is a real number. So from here we know that the diagonal elements, all the diagonal elements, they must be real. For an Hermitian operator, the diagonal elements must be real. Okay, so a quick question. I mean, in questions like these are very common in net exams. So you could be given 4 options. Okay, in 4 options you could be asked, identify the Hermitian operator. Okay, if you keep this in mind, then you can identify it very easily. Those kind of problems you don't have to actually work out. Okay, we don't have to work out really and find out, slog it out and find out whether which of these, for each and every one which is Hermitian. You just look at, first thing that you do is look at the diagonal elements. Those ones in which the diagonal elements, they are real, those matrices in which the diagonal elements is real, that must be a Hermitian matrix. So if you have, let's say, 4 options, out of 4 options, 3 of the options you find a complex number, okay, in the diagonal elements, then those 3 are ruled out. The one which does not have even one complex number in the diagonal, that must be an Hermitian matrix. So let us say A nu mu, okay, these are the matrix elements of A which corresponds to the Hermitian operator A. And as before, we have C. C is the column vector representation of a vector. So psi is a function. Psi can be written as a linear expansion of a basis, and those coefficients, okay, in the linear expansion, you collect those coefficients and you make a column vector. So that is going to be this. So just to help you recall, so we have psi, and this psi can be written. So suppose we have the basis. The bases are phi. Okay, the phi i's are the basis. So psi can be written as A1 phi 1 plus A2 phi 2 plus, okay, I am using C here, so let's say use C1 phi 1. So C1 phi 1, C2 phi 2, C3 phi 3, right? Then you just collect this C1, C2, C3, you just collect them together. Okay, so we have C1, C2, C3, you collect this together. So this gives us your column vector representation. So this contains all the information that is there in this. Okay, so C is the column vector representation of this vector psi. So that's how I've written over here. Okay, so psi can be written as C nu psi, C nu phi nu. So remember here, this is the Einstein's summation convention. So that means this is the same as, because there is a repeated index, mu is repeated. So what does this imply? It implies that there is a summation over here. Okay, so this is C nu phi nu. This is a summation over nu. This is understood. Okay, so hence this expectation value that you have, the expectation value, so we have psi is equal to it is equal to the scalar product of psi and a psi. Now you expand this. Okay, let me erase this a little bit over here. Okay, so let me just erase this a little bit here. So what we are doing over here is basically this. Okay, so what we are basically doing over here is we are having this one, there is a summation. Okay, there is a summation over nu, C nu phi nu. Okay, and then we have a, and this a on this side there is a another summation. There is another summation going on over here. Okay, so this summation is C mu phi mu. Okay, so because of this repeated index, so that means there is a double summation over here. This is summation over nu and this is summation over mu. I have not written this, but if you want to explicitly write this, this is what happens. So what we have here is a double sum. Okay, so instead of writing a double sum here, I just write it as nu mu. Okay, it's understood that this is actually two sums. And then we have C nu star, and then we have over here phi nu a phi mu and C mu. Okay, and this is going to give me the elements. We have already seen this. This is going to give me the elements of the matrix which represents this operator A, and that's how we get this one. Okay, so this is going to give us again a double sum. So summation over nu mu, so C nu star, and this we can call it as A nu mu and C mu. Okay, so this is actually the elements which we are getting it from over here. We provide this. Okay. Okay, so this particular equation can be written as a matrix multiplication of three matrices, because you can see here C nu star, that means you are taking the conjugate and you are taking the transpose of that. Okay, so this is so what we will do is, because C is a column matrix, so when you take the conjugate and you are taking the transpose, then this column matrix is going to become a row matrix. So that's how you get this as a row matrix. Now this one is going to be a 1 cross n matrix. This is a 1 cross n matrix, and this one will be an n cross n matrix. This is an n cross n matrix, and finally this is going to be again another n cross 1 matrix. So you can see here this n and this n, this 2n will get absorbed, these two n's will get absorbed from the rules of matrix multiplication. So what is going to be left behind is 1 and 1 here. So that means this A is going to be a 1 cross 1 matrix. That means it's basically a scalar. Okay, so this one, okay, this one we can write, because we have here what we have done is we have taken a transpose, as well as a conjugation. So transpose and conjugation means this is nothing but your C dagger, and this is, of course, this is your C. So C dagger AC. So your expectation value of a Hermitian operator, can be written as C dagger AC, where C, the C is a column vector which represents the vector which we are taking. So this vector could be a wave function. So we could have a wave function. That wave function you represent this as a column vector, and then you take the dagger of that, and then you apply this like this. You do this matrix multiplication. That is going to give us the expectation value of that Hermitian operator. So this is a self-adjoint 1 cross 1 matrix. So we can show, I leave this to you as an exercise. You have to show that C dagger AC, okay, C dagger AC is self-adjoint. I leave this to you, okay, just try this out on your own. You have to show that C dagger AC is self-adjoint. So I think I'm done with this topic on self-adjoint operators. In the next lecture we will do first a brief review of matrices, and then we will see some eigenvalue problems. So with this, I bring this particular lecture to a close. In case you have any queries, please feel free to get in touch with me. Thank you.